sesión de este curso de pruebas asistidas por computadora. Ahora vamos a escuchar al doctor Jean Philippe Lessard. El doctor Jean Philippe Lessard también es un viejo conocido de mi parte. O sea, él estudió doctorado en Georgia Tech bajo la dirección de Konstantin Mishaikov. Después hizo varios postdoctorados en Ámsterdam, en el Instituto de Estudios Avanzados en Princeton y en Rutgers. Y después de eso fue profesor en la Universidad de Laval y ahora, desde el año pasado, es profesor en la Universidad de McGill en Montreal, Canadá. Y entonces, bueno, pues es un placer tenerte aquí, Jean Philippe, y por favor, adelante con parte del curso.
Thank you very much, Renato. Thanks to everyone to stay here late. I mean, for me it's late, but for you guys it's kind of early, I guess. 5 to start a lecture at 5 from 5 to 7. That's wonderful. I like it. Actually, what Renato didn't mention is that I spent 1 year in Spain and I got accustomed to that rhythm where everything starts later and finishes later. So I love it. So I'm happy to actually give a talk late. Okay, so basically, Jay did such a wonderful job at actually introducing the general approach that what I'm going to do is only one example, but in the context of a slightly, say, harder problem. I mean, for geometric PDEs. So I'm going to restrict myself to a very specific problem, and for that problem, I'm going to look for very specific solutions, and that's going to lead to a problem which I'm going to basically solve using the tools that Jay talked about. But that's going to lead to an infinite dimensional map. And then in that context, and I'm going to really follow each steps of the bound. I mean, each bounds are going to be computed. I'm going to derive them. So the last part of my talk, I will show the bounds on the slides, and I will show how to implement them. I will show you some MATLAB code, which is going to use also IntLab. So I'm going to do some live computer-assisted proofs, and then at the end, I'm going to hopefully convince you that what we're doing is actually working for some not so trivial problems. But the example I'm going to talk about, I'm not saying that what I will propose today is the only way to do it, but it is, I chose that presentation and that specific type of approach to show that, I mean, in the simplest possible context, a nice application of the method that Jay talked about. So it's really important to realize that it may not be the best way to do it, but I think it still leads to some nice setup. And then, in fact, the setup that I'm going to present today is really going to come back tomorrow and on Friday. And tomorrow I'm going to focus a little bit more on delay differential equations, which are infinite dimensional dynamical systems. And with a very similar idea, I'm going to show how to prove existence of periodic orbits in delay differential equations with precisely the same kind of setup. So today I'm going to emphasize each step, and I'm going to do a lot of details, whereas probably tomorrow I'm going to do something similar in the context of Fourier and delay equations with a little bit less details, and on Friday I will probably do more applications without going into so many details. So today you're going to have to bear with me that that I'm going to do a lot of details and hopefully don't get discouraged. And there will be lecture notes that will be posted, and I'm following closely work that we've done in 2015 in the summer school in the West in Canada. So that was in Vancouver. So they organized these 3 weeks summer school, and we decided to find problems so that undergrads could solve. And what I'm going to show today is one of these problems that the undergrads solved after three weeks of pretty intense work in the summer school. So this is basically the output of that. So that's also a nice message that, this field is new, and yet it's exciting, and we can get non-trivial problems, and yet there are a lot of interesting problems that can be tackled even with people without a lot of background. So there's, of course, a variety of different problems that we can work on, but the one that I'm going to talk about today, hopefully, some people can work on some similar problems and then yet get some interesting results. Okay, so what I'm going to talk about today is basically a geometric PDE. So I have U sub t is equal to the Laplacian of U. It's a nonlinear elliptic boundary value problem. It's going to lead to a nonlinear boundary value problem, but it's the following problem. So I have U sub t equals the Laplacian of U plus lambda U plus U squared equals 0. And I want to solve that problem on a sphere, okay? So that's going to be my domain. So I have the two sphere. So solutions are going to be posed on the two sphere. And what I want to look for are steady states. Okay, so that's we're going to look for steady states. So already there, the way it is written down, then that leads to an infinite dimensional dynamical system. So say you have an initial function defined on the sphere, and then as you evolve under that dynamical system, then that changes. And the first question, as Jay mentioned, when you study a dynamical system, is to look for steady states. So that's kind of what I'm going to focus today. And okay, first I didn't want to put equals 0, so that's my PDE, right? That's my rule. And then I'm already skipping to the steady state. So if I look for steady states, then I'm just looking for the right-hand side is equal to 0. Okay, so that's my problem. So that's already a restriction. So I'm looking only for steady states. So that's the problem I'm interested in. So that's a classical elliptic problem, and that's kind of some people may think of it as a nonlinear eigenvalue problem posed on a manifold, on a sphere. Okay. And another restriction that I'm going to do here is that I'm going to look for very specific steady states. Why? Well, first of all, we wanted to find back in 2015 some interesting problems that undergrads and early grad students could tackle. Okay, and so the assumption is that we're going to look for radially symmetric solutions. With a very specific assumptions on the type. So basically, we're gonna write solutions instead of writing them as functions of u depending on x, y, and z. I'm gonna use spherical coordinates. So I'm gonna have two angles here, and then the first angle is this one, so that's gonna be my theta, and the other angle is this angle, which is gonna be phi. So in general, just if I look for solutions on the sphere, then I'm looking for theta between 0 and pi, and phi between 0 and 2 pi. Okay? But if I'm looking for very specific radially symmetric solutions, so solutions, then there's a lot of things I can impose. So what I'm going to look for are solutions which will be symmetric in the equator, and that will be invariant under the action, the angle phi. Okay, so I'm going to look for solutions. So we look for solutions symmetric in the equator. That's the first restriction. So basically, and the second one, they are, I don't know how I framed that. They are invariant with respect to the rotation about the z-axis. So invariant with respect to the rotation about the z-axis. So that's going to lead to a couple of boundary values that I'm going to get out of these symmetry assumptions. Okay, so already at that point, I made a lot of assumptions, and I'm really only going to look for such solutions. So in order to actually make sense of these symmetric conditions, and I'm going to rewrite that problem here in spherical coordinates. So all I have really to do is to write the Laplacian, which is now going to be the Laplace-Beltrami operator on a sphere. So now that operator is really the geometric generalization of the Laplace equation, but now that's on a sphere, so that's basically the Laplace-Beltrami operator, Beltrami. And in spherical coordinates, that leads to the following. So that leads to 1 over sine of theta, the partial derivative with respect to theta of the product sine of theta times the partial of u with respect to theta, plus 1 over sine square of theta, the second derivative of u with respect to phi. Yeah. Okay, so that's the Laplace-Beltrami operator. And so basically what I'm now looking for are solutions. So now I just replace this. So if I write plus lambda u plus u squared, so what I have is a plus lambda u that depends on phi and theta plus u square that depends on phi and theta. And I'm looking for the zeros of that. Okay, so now it's now the same equation, but now really expressed in terms of spherical coordinates. And now that's where the assumptions on the symmetric, the fact that now I am looking for specific type of solutions, is something nice happens in the Laplace-Beltrami operator, and it is the fact that this is now going to be 0. Why? Because there's no dependency on the phi. I mean, I'm actually, that's equation number 2. So because of equation number 2, that's going to 0. That's because of number 2. And for number 1, sorry, then I'm actually going to append an equation for that new problem. So I'm basically going to have a boundary value problem. Okay, so that's equal to 0. And now when I actually do that derivative here, so if I write that down, so that's the derivative of sine, so that's cosine, so that's cotangent of theta times u prime. So now I'm going to get rid of phi, because phi is no longer a variable here. It's the function u does not depend on phi, so that's basically that assumption here. And I have now plus sine of theta divided by sine of theta times the second derivative. So the second derivative, since I do not have another variable, so that's really just the second derivative, plus lambda u of theta plus u squared of theta is equal to 0. So this is my boundary value problem that I'm, well, not yet. Okay, so that disappears. So I'm looking for the zeros of that. And now since I'm looking for solutions which are symmetric in the equator, that means that at that value, I mean the value when theta is equal to pi over 2, then the derivative there is equal to 0. So what I impose is this. And also the fact that I have invariance in the rotation, I need that, I mean, I'm actually appending that equation as well. So u prime at 0 is equal to 0. So that if I actually go there, or there, it's the same. But it's coming from the fact that I have the z invariance. Okay, so at this point, now I have a problem to solve, which is what? Which is a non-autonomous second order nonlinear equation with boundary values. Okay, so basically at that point, this is the problem I'm interested in. So at this point, you may say, well, okay, so now this is a finite dimensional problem. It is, but the way we're going to set it up, that's going to lead to an infinite dimensional problem, because the unknown here really is a function that goes from the interval 0 to pi over 2 into r. So that's a function. So that we're going to look for functions. So that's why it's an infinite dimensional problem. But if you go back to the origin, that really is looking for steady states of geometric PD on a sphere. And then what I'm telling you today is about this very specific problem, and I'm going to use now the techniques that Jay introduced in order to solve rigorously that problem using the computer. But I mean, you could actually modify, I mean, we haven't done it, but let's say there's a lot of people in PDs that are interested in different type of nonlinearities here and different type of linear operator. And by modifying what I'm talking about, I think that there could be a lot of interesting new type of results that we could tackle using the ideas I will talk about today. Okay, so I already made a lot of assumptions. I'm going to make another one, which is kind of strong. And it is the fact that I'm assuming that solutions to that problem can be written down as a Taylor series, which is a very strong assumption because I'm assuming that I can get all the way to pi over 2. So basically, since I want to find an easy setup, and I don't want to go into too many technical details, I want to find the simplest type of say, numerics and rigorous computation so that I can solve that problem. And we decided to use Taylor series in that summer school back in 2015 because we really thought that, from our perspective, that was the easiest kind of problem to solve with the least, let's say, necessary background. Okay? But in order to do that, yep.
Do you have to include the periodicity of u?
The periodicity of U, no, we don't have to introduce that, no.
But you want that the solution have the periodicity of 2 pi?
Well, in that case, the 2 pi is no longer depending on 2 pi. I mean, that's gone.
Well, not 2 pi.
So the theta.
You're only solving for the theta between 0 and pi over 2, right?
Yeah. Yeah, so here this is really just for theta between 0 and pi over 2. That's kind of a boundary value problem, where at pi over 2 I'm imposing the symmetry condition so that I can afterward take that part of the solution and then just mirror it through the z-axis. Okay, so I'm already telling you how I'm going to solve that. I'm going to solve that using Taylor series. Okay, but in order for that to actually, so what we did first, we just plugged power series there, and then that led to, for instance, having to satisfy that condition. And if you think about what that condition means in terms of Taylor series or power series, then there is a pi over 2 to the power n appearing, and that's a number greater than 1, and that made everything super unstable numerically. So then we decided to change the setup just by introducing a rescaling in order to stabilize the numerics. So that's the kind of thing that when we do this type of computer-assisted proofs, there's a lot of choices to be made. And sometimes we have to choose the setup of the problem in a way that it's going to make the numerics nicer and easier. And that's already one example here. So instead of solving that, we introduce a rescaling to stabilize the numerics. Okay, so the rescaling is the following. It's nothing fancy. So basically we introduced v of var theta. By definition, that's pi squared divided by 4 times u of pi divided by 2 var theta, and a new parameter lambda is equal to pi squared divided by 4 times lambda. Okay? Why we did that? Because we wanted basically now to have the new variable to be between 0 and 1. Okay? So by plugging that in this boundary value problem leads to the following equivalent problem. And actually I'm going to write it here because I don't want to erase it, because later I will have the bounds, and then so this is like the important problem. Okay, so this is the second derivative of v plus pi over 2. And then what I'm going to do is that I'm going to rewrite this problem a little bit I'm going to basically, so if you look at cotan here, when theta is equal to 0, there is a singularity here. Okay, and that singularity, I'm going to put it there, and then I'm going to use the fact that I have that condition that will resolve the singularity. And now I'll be left with something that doesn't have a singularity. It's going to be a non-autonomous problem. I would have to do analysis to actually control that part, but that's something that we always do. That's fine. But basically, I'm just going to rewrite it in the following way. So it's the second derivative of v plus pi over 2 var theta times cotan of pi divided by 2 var theta times v prime theta divided by var theta, and the rest is just plus lambda tilde v of var theta plus now v square equals 0. Okay, so that's that trick now makes it so that the singularity is here, but that's going to be resolved again by that condition. And that the two boundary values now are somehow very similar. So it's v prime at 0 is equal to 0, and v prime at 1 is equal to 1, to 0. Okay, so I'm going to call this problem P. So now this is the problem that I want to solve using the IDEs that Jay talked about. Okay? So I'm really looking for a 0 of that nonlinear boundary value problem. And okay, so then the big assumption is so as I said, is that now I'm going to assume that solutions to P can be expressed as Taylor series. So assumption, and that assumption need not be there. It will lead to an easier problem to solve, and that means that we will only be able to do some solutions. But if I was extending, or if I was like considering different type of numerical methods to approximate that, I could compute much more. But that's the assumption that leads to say, an easy infinite dimensional map, okay? So assumption is that solutions of P can be expressed as V of var theta equals the sum an theta, var theta to the n.
The problem is to expand in Taylor series close to the singularity because you don't know it.
Yeah, so this is
Irregular in that.
right. So that's going to be fine. In fact, that has geometric decay of Taylor series of a constant divided by 2 to the n. So that's fine. Now this is going to be this problem, but if you think of power series, if I impose that in a power series, that's going to resolve the first guy, which is not nice here. I mean, I'm going to do the details here. Okay, but that's a very big assumption. So you have to keep or bear in mind that if I actually wanted to solve this problem at any cost, and if there was $1 million problem associated to find all solutions up to lambda tilde equals 1,000 or something, I would not use that approach because there are points for which it is just not satisfied. I mean, in fact, when we have some solutions and I increase the parameter lambda, then solutions become more and more complicated, and in some sense, the poles are getting in the unit disk, so then that just fails. So then if I wanted to continue these solutions or to do something else, I would have to do something more sophisticated, maybe solve that using power series on a smaller interval and then do something else on the rest. So that's all basically possible. But again, this is the assumption that will lead to a nice infinite dimensional map posed on the coefficients, the Taylor coefficients. These will be my new unknowns, okay? So now what I want to do from now on is that I want to write an operator on a Banach space which will basically enclose or like characterize the solutions to that boundary value problem. Okay, so now what I want to do is that go design a problem of the form f, I'm going to use a in that case, f of a equals 0 on some Banach space X. And then I want to use the machinery that G talked about. Okay, so here there is, I mean, you can already see that there's a lot of choices that we have to make in order for, I mean, a given problem to be solved using the techniques that we were trying to present. So we start with a very general problem, and then we reduce it to something, I mean, there's a lot of steps from the original PDE steady state problem into that one, and there's a lot of choices. And in fact, now I'm going to choose a Banach space which will facilitate the nonlinear analysis. Why? Because if you look at that problem, it's a non-autonomous problem. It's nonlinear. So when we actually do these bounds, we have to compute, say, products of functions, and then we have to actually multiply things together, and we have to make sure that we can do not only the linear, let's say we don't only have to bound linear operators or norms of linear operators. We also have to handle the nonlinearities. So we always have to choose a space so that we can do linear analysis and nonlinear analysis, and that's going to lead to, I mean, I'm going to start by introducing the Banach space in which we're going to work. Okay, so that Banach space is basically motivated by the fact that what I'm going to have, so I'm going to plug that in there, and once I will plug that in there, then I will have to solve for Fourier coefficients of the resulting map, and then the Taylor coefficients of the resulting map, and now I'll have Cauchy products, okay? Because I will have products of V with itself. So when I take two power series and I multiply them together, the coefficients of the resulting power series are Cauchy products, okay? So that will, I mean, now that's going to justify choosing the Banach space that I'm going to introduce now. Okay, so the Banach space. So what do we choose for this? So I want to be able to enclose, I want to have a Banach space of Taylor coefficients. But because I rescaled my domain, then now I'm looking for solutions with converging Taylor series on the entire interval 0 to 1, which means that for that to happen, I'd better have analytic or geometric decay for the A sub n's. So I'm going to choose a space which will represent analytic functions and which also has a property that it allows me to control nicely the Cauchy products. Okay, so Banach space is going to be the following. So it's X will be L, what I call nu 1. So given a number nu greater than 1, and it's greater than 1 because I want to have converging Taylor series on the interval, var theta between 0 and 1. Okay, so that's the set of sequences corresponding to my Taylor coefficients such that the norm of that, which I will define here. So by definition, the norm is a weighted L1 norm, and I'm assuming that that norm is actually finite. Okay? So that's a very natural space to choose, because in that space I do have geometric decay. I mean, if you have an element in that space, so given, say, A, so if A is in L nu 1, then you know that for any component K, then if I have this here, this is less or equal than the sum n greater or equal than 0 of A n nu to the n, right? For any given K, I have this. And that's exactly the L nu 1 norm, which is finite. So that's finite. Basically, it means that AK is less or equal than a constant, which is the L1 norm, the weighted L1 norm, divided by nu to the K. So we can see that the coefficients, they do have a geometric decay. So that's geometric decay. Okay? So it really makes sense to consider that for the space that will enclose the solutions I'm looking for. Okay? So, as I said before, I will not do that now. I want to talk a little bit about the Banach space. But after I talk about the Banach space, I will move from that problem into an equivalent problem, f of a is equal to 0, where a will correspond really to the infinite sequence of Taylor coefficients. And there I will solve that problem in L nu 1. Okay? But let me just give a little bit more details about the nice properties of that Banach space. So first of all, it is a Banach space. It is not a Hilbert space. Okay? And if I have a sequence in L nu 1, then by defining a power series given by these coefficients about, say, some numbers in a complex plane, then that gives me an analytic function. Okay, so let's say properties. I mean, the first one is that if A is in L nu 1, so let's say again I take nu greater than 1. So given an infinite sequence about in L nu 1, then if I let f of z, and also I take, say, a z0 in a complex plane, so I define f of z to be, by definition, the power series. So that's a sequence that has infinitely many Taylor coefficients. So if I define it like that, so this is going to be an analytic function on the open disk centered at z0. Yes?
Is nu an integer or are you?
Which one? Z0?
Nu.
Yeah, nu is real.
Real.
Yeah, is a real number. So letting that by definition, then what I have that f is an analytic function defined on the open disk centered at z0 with value in C. Okay. So, and the proof of that is actually easy, and I think it is enlightening. So the proof of that is that if I take the soup norm of that function, then this is just the soup over the z such that they are in that open disk. So that's basically saying it's the soup of all the z, so that z minus z0 in complex module is strictly less than nu. So that's what it means here, of the complex module of f of z. By definition, this is the infinite sum of an is z minus z0 to the n greater or equal than 0, and still I'm looking for all the z so that that equation is satisfied. Now I can apply the triangle inequality. I'll have the an in complex modulus. I'll have z minus z0 to the power n in complex modulus. This is less or equal than the complex modulus of z minus z0 to the power n. And then because of the fact that I am actually in the disk, that's going to be less than nu, right, to the power n. So this is exactly less or equal than the L nu1 norm. And this is, well, by assumption, this is finite, okay? Well, what does that mean? It means that the power series, I mean, the function that represents f as a power series converges on the open disk, so therefore it is analytic on the disk. So I have my proof there. And another nice characteristic is that if we actually, from this, is that when we will do computer-assisted proofs in that space, well, every proof that we get and every error bound that we get from the computer-assisted proof will give us also a C0 bound, which people somehow often prefer because that's much more, I mean, you're much more close to the function that you're trying to approximate, right? Whereas because, I mean, I will have this problem and I will move to a map posed on Taylor coefficients, but I would still like to have some sort of bounds that allow me to go back to say the C0, C1, or C2. Well, in that case, it's C0. But that's a nice feature. So that proof, I think, is interesting also because we can see that that the bounds that we'll get from the proof give us more natural control. Okay, so now another property is that, as I said, we will do some nonlinear analysis. And L nu1, well, that's a very nice property, is that it is a Banach algebra under the Cauchy product. And that's going to be very useful for the nonlinear analysis, as I said before. Okay, so first let me recall what the Cauchy product is. So let's say given, so let's say I will write that as a definition. So given two sequences come on, A and B. Well, they don't necessarily need to be in L nu1, but if they are, then we do not have any problem with convergence. Then their Cauchy product is given by the sequence that I denote by A star B, and that is a sequence, so component wise, but it is given by the sequence whose components are okay, so it's A star B sub n, so the Cauchy product is the sum k goes from 0 to n of A, k, b, n minus k. So that's the Cauchy product. And another way to write it, which I'm going to write it like that because tomorrow I'm going to do Fourier analysis, and then when I will have two products of Fourier series, that's going to lead to not a Cauchy product, but to a discrete convolution. But the same properties of Banach algebra under that product will hold as in here. So I'm going to rewrite it basically as follows, so that it basically opens the it opens the way for tomorrow. So it's AN1, BN2. So that's the set of all possibilities. So given n, so that's all the possible n1 and n2. And for Taylor series or for Cauchy products, the n1s and n2 are positive. So they are basically between 0 and n. Okay? But tomorrow I'm going to have Fourier series, and that's going to be exactly the same kind of product. I will have discrete convolution. The difference will be that now that will be possible for the n1 and n2 to be negative. So So I'll have bi-infinite sequences of Fourier coefficients, and I will take their discrete convolution. But what I'm about to write in here, I'm going to have exactly the same notation for the L nu 1, but it's going to be in context of Fourier. Okay, and with these kind of spaces, we can already do a lot of different nice applications. Okay, and so that's the Cauchy product, right? And now I'm going to go to the second properties, is that L nu 1 under the Cauchy product is a Banach algebra. So is a Banach algebra. So it may sound a little scary for those of you who never saw or heard the name Banach algebra. The only thing which is more, so it is a Banach space. So that's what is important. Okay, so it's a Banach space. In fact, this is, if you go here, then, I mean, you can go and then show that, in fact, every Cauchy sequence converges using that definition of the norm. That's not so hard. That's kind of standard functional analytic, I would say, exercise. Now, the extra feature is that it is a Banach algebra. So what is the extra feature of a Banach algebra? Is that, first of all, you have now a multiplicative, I mean, the Banach space is vector space. So there's not necessarily possibilities to multiply vectors, whereas here we do. So on top of the linear and the additive properties of vectors, then we can multiply them. And with that, it becomes an algebra. So you take two sequences in the space, you multiply them together, in that case by the Cauchy product, and you stay in that space. What does that mean here? It means that if you have two, I mean, A and B in L nu 1, but by what I showed you before, they both have algebraic decay. So you take that, you multiply them together, and you will still have this algebraic decay. Okay? And so what does that mean here in terms of really the extra thing we have to show is that A star B, the L nu 1 norm, is less or equal than the product of the norm. Okay, so that's really the extra thing we have to show. When you have a Banach space, you put a multiplication on the Banach space, and if you want to show that you have a Banach algebra, that's essentially what you have to show. Because if you show that that's the case, then clearly it is an algebra, because if A and B have finite norms, then it must be the case that A star B also has finite norm. Okay? I'm going to prove that very quickly.
So the constant is always 1, right? So
well, if it was not 1, then you could tweak the norm so that it becomes 1. Yeah.
excuse me.
Yeah.
Inner product, can we consider the Banach operator as case?
So inner product in that case, well, the inner product takes two vectors and returns a scalar, right?
That's right, yeah. Sorry.
That would be more like a bilinear function or something. But in that case, this is really like you have two vectors and you return a vector. It's like the cross product in R3. Two vectors, you return a vector. But now in that case, it is more of a, I mean, I don't know what else to say. Is there something smarter I can say? Okay. Okay, so let me actually prove it, because these kind of things, so now I'm giving you all the details, because I also want to actually make sure that you understand that we're actually doing math here. We're not just pressing a button to do the proofs. And these kind of things are really necessary for us to, and that's a choice, right? Because I could have chosen L2 or L infinity. I mean, I spent 5 years of my life when I was a PhD at Georgia Tech to do all of these proofs in L infinity. It turned out that was much less cute. We had some constants and we had to suffer, and then I suffered, and you know, but then I realized this way later, and then I thought at some point that I lost 5 years of my life, but then Jay said, no, don't worry, there's these nice applications. And then in some context, these other L infinity norms are useful, but that's very nice. So, okay, let me do the proof. So I have to compute so let me just write it down. So I have two sequences. So let's say I have to take, okay, so first A and B, I start with two sequences, and you can think of them as Taylor sequences. I multiply them, and I take their weighted L1 norm. Okay, by definition, what is this? This is the weighted L1 norm of A star B sub n, where that's the Cauchy product, nu to the power n, when n is greater or equal than 0. Okay, so what is this? Well, I'm just going to use the definition of the Cauchy product. So that's n greater or equal than 0. Now I have the sum, k goes from 0 to n, of a, k, b, n minus k, everything nu to the power n. So I could have done actually this presentation with a much more general weight. Now I chose the weight to be an algebraic, a geometric weight. I could have chosen different type of weights. The reason why I chose this one is because in that case we're going to use Taylor series. But if I was using a different type of basis with slower decay rates, or say algebraic decay rates coming from, that could be motivated from the fact that I would have from the data of the problem some not so regular problems, so that the solution is not so regular. So in that case, I could have been forced to take something which decays slower. And then I would have had a different weight here. But really the key in choosing the weight is that I can do something like this. So now, in that case, I just write nu to the power n as nu to the power n minus k times nu to the power k. Okay? So if I had weights that were allowing me to do something sub-additive, so if I had that, now I have basically that nu to the n is equal to nu to the n minus k times nu to the k. Well, if I had something slightly more general, or if I wanted to use a different decay rate or different weight, so if I had a more general weight, all I would need is that assumption on the weights in order for that argument to carry on. Okay? So I could choose some weights with some algebraic, I could, instead of geometric growth, I could choose some algebraic growth here, which would correspond to some functions which are described by coefficients that are decreasing geometrically fast, algebraically fast to 0. That's very useful in different problems. Okay? But as long as you have this, then I could replace that argument here by some omega with some general weights with some algebraic growth. As long as it satisfies this, then I'm good. And then you can see here that not only satisfies this, but it's actually equal. Okay? So I have this. So that was my small parenthesis to say that also we can enlarge the type of these can be more general, and we can also apply that to some geometric algebraic decay rate. Okay. So this is less or equal than what? Now I'm going to put everything inside. I'm going to say, well, this is the sum, n greater or equal than 0. I'm going to use some triangle inequality, ak nu to the k. This is k equals from 0 to n, and then times b n minus k nu n minus k. So when you actually look at this right now, well, now I have some restrictions on the k's because I'm only summing them up to n, right? But if I was removing that restriction, if I was just saying, well, let's sum all of them, now I have the same thing. Now I have a shift. But let's say if I was just removing all of the constraints, I would just have that this is less or equal than, well, n greater or equal than 0 of an nu to the n times the sum n greater or equal than 0 of bn nu to the n. So basically that just removes absolutely all the constraints that I had on this level. Okay? I'm basically just adding more terms here. And that's precisely the L nu 1 norm of A times the L nu 1 norm of B. So that's the end of the proof. Okay? So these are the kind of things that if we didn't have that, we would have to get some constant out. If we didn't have this weighted L1 norm, then we would potentially have to work harder to get some constant out, because in these computer assisted proofs, we want to get all the constants out in order to prove that in the end you do have a contraction. Okay, so that's kind of my theoretical background on the choice of the Banach space, and these two properties are going to be quite, that really is the key to that choice of space. And also the fact that bounded linear operator defined on L nu 1, because it's L1, then we can use the fact that the dual of L1 is L infinity. It's also weighted, it's a weighted L infinity space. And by knowing the dual, then there's a lot of nice features that we can use to bound and to control norms of linear functionals and norms of linear operators.
Excuse me.
Yes.
I have a question. In the second to last expression,
Here?
There you have a k.
Yes.
That is outside the sum of k equals 0 to n.
Here.
No, yeah. But there, what's the value of that k?
So, it's only for the case so that k is between 0 and n, right? So So what I'm doing here is that I'm just summing the b where, I mean, basically when n equals 0, I mean, that's going to be b0, but it's only going to go from 0 to n in the end. But if I remove that constraints on the b case, then, I mean, I'm left with all of them. And that's why I do have a Banach algebra. And in fact, this is surprisingly tight because you can find a lot of examples where this is an equality. So this is not like losing so much. It's very nice. It's very useful, and it's surprisingly not a lousy estimate. Okay. Okay. So now I'm ready to now introduce an operator f. Actually, not yet. One last.
Is there any estimates on the derivatives?
On the derivative of. Well, at this point, I still didn't move to the space of Taylor coefficients. Now this is what I'm about to do. But before doing that, I better know how to control the Taylor coefficients of that function. And that's my next little lemma, or yep. And that's actually a nice, a nice exercise to actually compute the and to rigorously compute the Taylor coefficients of that map of that function. So it's a fact. It's not really a lemma. So fact. So pi over 2 var theta of cotan of pi over 2 var theta. This is expressed as Taylor series Vj var theta to the j, where, and in fact we had to look, I mean the students in the summer school, they actually had to look a lot for that formula, which was in the end the most useful for us. So where Bj is equal to 1 when j is 0, it's equal to 0 if j is odd, and then it is equal to minus 2 times the zeta function, now it's a matter of writing it down, okay, of j divided by 2 to the j for j greater or equal than 1 even. Okay. So that's the zeta, the Riemann zeta function. So this is the sum n greater or equal than 1. So is the Riemann zeta function. Okay. So that leads to a bunch of, so that's another, say, that's another part where, you know, what we want to do is that we want to modify that into the problem of looking for a 0, and we want to have chances to be able to succeed. So if we write that as a power series, but or if we write it in a different way so that the convergence is very slow, and that's not useful. So we basically wanted to have that, to rewrite the problem so that the non-autonomous part would decay fast. And that's what we have here. Because if you look at the Riemann zeta function, I mean, so what we're going to do basically is that we need to compute that, and we need to compute that rigorously if we want to compute or to get proofs, right? So if you look at that, well, for when j is small, so in that case we're going to have, let's say, when j is equal to 1, I think there's a 2j there, because otherwise it's not converging. Yeah? I think there is a 2j, because then it is, okay, j is even. Okay, that's good. That's for j even, because otherwise if j is equal to 1, then that's not converging, okay? But we know, for instance, that in the tail for very large j, then we can use the upper bound, so that's going to be, that's a geometric decay right here. And we know that for very large j, then for instance, this is always less or equal than pi squared divided by 6. Because, I mean, the useful fact is that phi of s is always less or equal than zeta of s is always less or equal than zeta of 2, which is pi squared divided by 6. So for very large data, then we're going to use that bound, I mean, basically to get a constant divided by 2 to the j. But for the finite, so that's for s large enough. But for small enough j, then we'll have to compute a lot of coefficients in that sum and then bound the tail. Yeah, I'm going to briefly talk about that later. Okay. So now we have a power series expansion of the nonlinear term, the non-autonomous term. That's going to hit this, and then we're going to get a Cauchy product of this. Okay? So now I am actually ready for my to move and to introduce f of a equals 0. So now I'm going to introduce it, f of a equals 0, to be solved in L nu 1. So before I do that, one last comment. So I have some restrictions on nu. I already told you that nu needed to be greater than 1 in order for my power series to converge, because my domain of my Taylor function is on the interval 0, 1. But I have another constraint. What is it? Haha, now I'm being a professor now. What is my other constraint? So I cannot do, I will have restrictions on nu. I cannot take nu too large. Why is that? Because when you think about power series, then the radius of convergence of that can't be greater than 2, because I have the decay rate here is basically 2 to the power n, right? So because of that, when I will have a power series of this, then this is at most, I mean, this is in fact in L nu 1, but nu has to be less than 2, because otherwise I will, okay, and since I have an algebra, when I will move to Cauchy product, then I will have the Cauchy product between B and that function, okay, and then I will lose 1 degree of regularity. But basically, because of the fact that I will have this term and I have an algebra, then that cannot be in L nu 1 with nu greater than 2. If it was, then I would not converge. So basically, I won't be able to solve in a higher regularity space because of the algebra, I would get out and I would blow up, right? So the restrictions I will have will be nu between 1 and 2. So that's the kind of Banach space I'm gonna. So that's and then that nu, that parameter, we'll fix it in practice. Okay. Okay. So now I want to get a map posed on the Taylor coefficients, so that if I can solve that in that Banach space with that restrictions on the weight, then I can get a solution, a rigorous proof of the solution of that. And if I go all the way back, I will have a steady state of the geometric PDE posed on a sphere. That would be a computer-assisted proof. And the bound, say if it's 10 to the minus 8, that would give me a C0 bound for the location of the solution on the sphere. Okay, so what do I do? Well, I just plugged, I mean, we did that probably in your first ODE class, right? Power series method. So now it's a singular problem. It's power series method. I just plugged that in. But for most problems you did in your first ODE class using power series, you didn't have that problem, right? You didn't have to solve, we didn't have a nonlinear term. I mean, well, that's more complicated. It's nonlinear, but I'm pretty sure that you did a lot of these. So what we do? Well, we just compute formally. So if I have that power series that I erased, so now I'm actually, okay, so that's my sum, right? So I'm assuming that this is solution. So let me just differentiate it formally. So that's the sum greater or equal than 1 of n times an times var theta to the n minus 1. I just differentiate and I do everything formally. Same thing with the second derivative. Well, that's just the sum. Now I start from 2. N times n minus 1 times an times var theta to the n minus 2. So that's going to be this term here. Now here I have the product of that function, which is, I mean, that sum here is bn theta to the n greater or equal than 0. And what is this? So this is, okay, so I'm going to rewrite v prime of var theta divided by theta. So this is what? This is, so v prime is this term, so it starts at n equals to 1. So the first term is a1. Okay, so I have a1 divided by var theta plus the sum n greater or equal than 2 of, now I have this, but then I have n an var theta to the n minus 2 because I divided by theta here. Okay, so that's the singular term. And this is precisely where if I impose that condition in my problem, then I impose what? I impose that v prime, which is at 0, equals to what? What is v prime at 0? It's 0, but what is it in terms of the Taylor coefficient? It is a1, right? So it means that that condition, if I impose it, it forces a1 to be 0. So on the level of solving, that resolves the singularity, if I impose that in my map. Okay, so I will append that in my f. In fact, the first component of my f will be a1, which will be forced to be equal to 0, because that's the problem I'm solving. Okay, so that's my second, that will be my second guy. So I will have this times the b end, and plus, well, I will have lambda times v plus, that's going to be just the Cauchy product. So v square of theta, this is now n greater or equal than 0 of a star a sub n, that's the Cauchy product, theta to the n. So that's really when you have two power series, you multiply them together, and you do get that their Taylor coefficients are the Cauchy products. Okay? Now, I will have everything basically shifted and starting at 2. So I will rewrite that as the sum n greater or equal than 2 of a star a n minus 2 var theta to the n minus 2. Okay. So now when I plug my power series in my nonlinear boundary value problem, then I'm going to get the following relation. So P becomes what? So I'll have sum n greater or equal than 2 of. So the first element is the second derivative, and the second derivative is n times n minus 1 an. So it's n times n minus 1 an. So everything is going to be times n minus 2, theta, var theta to the n minus 2. So plus, so now I'm going to have the Cauchy product between b and n times an. So for sake of simplicity, I'm going to define an operator that I defined by j of an to be n times an. So that's just a notation. So that's kind of taking care of, that's kind of the derivative in Taylor coefficient space somehow. So that's my first term. Then I have the product of b, so I'm going to have b or j a star b n. So that's if you think in terms of Taylor coefficient, this is n times an, and that's the b here. So that's the Cauchy product of this term plus lambda, and then v tilde, well, lambda times v. So I can also start that sum at 2 and have n greater or equal than 2 of a n minus 2 var theta n minus 2. So I have plus lambda tilde times a n minus 2 plus a star a n minus 2. And I want that to be 0 for all. I want that to be 0, right? This is exactly my boundary value problem. And on top of that, I impose that a1 is equal to 0, which is encompassing that. And now I will have the other condition, and I want that to be equal to 0. So at the very beginning, when I had a boundary value problem posed on the interval 0 to pi over 2, I mentioned the numerical instability. So if I did not do that rescaling, that condition would have basically a pi divided by 2 to the power j, which would make that because now we're going to compute, right? So that would make this very unstable numerically. So that would decrease very fast, but that would increase really quickly. So then I would have extremely large number multiplying by extremely small numbers, and things are just more unstable numerically. So that was really the reason why we rescaled. Okay, so then I'm there. So now I have fa. I define that to be fn of a for all n greater or equal than 0, where my fn of a, by definition, when n equals 0, this is a1. That's for n equals 0. For n equals 1, that's the second condition. And for all n greater or equal than 2, I want that to be equal to 0. So I have n minus 1 an plus the Cauchy product between j times a star dn plus lambda tilde times an minus 2 plus a star a Cauchy product, but at index n minus 2, and that's for n greater or equal than 2. So now I have an infinite dimensional nonlinear operator posed on a Banach space, which is in that case L nu 1. So this is now the problem. So after all of that work, then we are in a spot where we can use J's machinery. Okay, so that's really just the beginning. Okay, so so then if I go back to J's, so I will stop writing soon, because at some point now I want to construct all the bounds. So that's going to be too much writing. So basically what I'm going to do is that I'm going to discuss a little bit about how to find a numerical approximation and how to find the approximate derivative, which was the A dagger that Jay talked about, but now in an infinite dimensional setup, which in that case is going to be a little bit more involved than taking a numerical derivative. And I'm going to introduce how to compute the approximate inverse, which will basically be the numerical inverse of the finite part of the approximate derivative, and the tail will be done theoretically. The inverse will be done theoretically. And once I will have the approximate solution, the approximate derivative A dagger, and the approximate inverse A, then I'm going to stop writing and I'm going to show the bounds, because that's a little bit more technical. And as I show the bounds, I will show how to implement them in MATLAB. And at the end, I'm going to stop. I'm going to show and do some live computer-assisted proofs, and we should see some nice radially symmetric solutions on a sphere. Okay, so I think I still have time, right? Otherwise,
6:26.
Okay. So maybe I will wait a little bit. I just want to do. I want to do the A and A dagger, and I want to do that probably. Actually, this I want to leave there. I will do that here. Okay. Okay, so I want to emphasize the fact that that example seems to be very specific, but the thing is that these spaces we're gonna use them for the rest of the week. These kind of weighted L1 spaces. Jay's going to talk about parameterization of invariant manifolds, and when we have fixed points and we can parameterize them using power series, Taylor series. So basically the spaces that we're going to consider for the proofs are really in these kind of spaces. Tomorrow I'm going to talk about periodic orbits in Dirac differential equations, which is really a not trivial problem because you're in an infinite dimensional function space, because that's an infinite dimensional dynamical system, and I'm going to solve that using Fourier. I'm going to plug Fourier series in the DDE, get a very similar problem to solve, but now instead of L nu 1 for Cauchy products, it's going to be L nu 1 with discrete convolutions. So it seems that this is a very specific example, but I think it showcases all of the ingredients that the problems to be seen in the next couple of days are going to be, basically. Okay, so first part, now we are at this point, we have a problem of the form f of a equals 0 on an infinite dimensional space. So I want to be able to compute a numerical approximation. So in that case, I have to do some sort of approximation or finite dimensional projection if I want to compute, right? Because that problem here has really infinitely many variables, so the Taylor coefficients, and it has infinitely many functions. So I better, if I want to compute, and using the nice ideas that G talked about in terms of Newton, then I better truncate that. So the first part is actually to compute or to consider a finite dimensional projection. Okay, so let's say computing an approximate solution. Solution A bar such that f of A bar is approximately equal to 0. what is important to realize here is that that's a non-local problem. That's a boundary value problem. So if you were to solve an initial value problem with Taylor, or if you were to solve what Jay will talk about tomorrow, which is going to find a parameterization of, say, a steady state, the stable manifold of a steady state for an ODE, then these problems are local, which means that when you write them in terms of their Fourier, their Taylor operator, I mean, there is basically a rule that allows you to compute exactly up to some given order the coefficients. Well, that would be the case if I didn't have that guy. Because if I didn't have that guy, which is basically my boundary value at on the right, which corresponds to the fact that I have this symmetry at the equator, then I could actually express or solve exactly the, I mean, I could, yeah, I would extract the nth component of A there, put all of that on the left, and then equal that to 0, and then have some explicit rule that would give me exactly the Taylor coefficients. And that's a very nice feature of Taylor when you solve local problems. But that's not the case here. So that's already a problem where we have to do some things, I mean, more sophisticated to actually compute and to do the proof. And that's why I think it's a good example to showcase that we have to find somehow, or finding an approximate derivative and a Ney-Dagger is kind of an important, it's a nice way to do things. Okay. So, we want to compute an approximate solution. That's always, yes?
In the previous case, you want that this series was equal 0.
Yeah.
And you compare to the last problem. But the main problem here is, if you get a solution of the 8, how do you know that the sum of the that you have there are convergent sums?
Yes. Okay. So what I will do is that I will choose a nu between 1 and 2, and if I do a proof, a computer-assisted proof of that operator, actually it's a good point. I should write a lemma that says that if I can find the existence of A in L nu 1 with nu between 1 and 2, such that f of A equals 0, then I will have that sum would converge uniformly because of the fact that I actually did prove that there is a 0 of that in L nu 1. So, I mean, it's a good point, and the answer to that is that you need nu between 1 and 2, otherwise you will not have enough convergence. So basically, if you prove that, then that is somehow going to be satisfied for all n, and then you'll have uniform convergence of that, and therefore that will, by construction, solve the boundary value problem. But there is a lemma that needs to be written here. But I guarantee you that once we have a proof, then we have uniform convergence of that, and that then, therefore, solves, by construction, the A solve the boundary value problem. Yes. But I actually wrote a lemma there, but now I realize that I was talking a lot, so the lemma is written there, but it's not, I mean, it's in fact in the lecture notes that I will provide to Renato.
And maybe you can show that the first sum is convergent, but the second sum of G multiplied by AG also.
Well, but that's a byproduct of the fact that I'm in L nu 1. If I consider vectors in L nu 1 and nu is greater than 1, I have algebraic decay. So that decreases algebraically fast, and that kills a J. So that sum converges. No problem.
You can think about doing Cauchy bounds on a slightly smaller disk.
Yeah.
You can bound derivatives.
Yeah, but basically that sum always converges if you take an input in L nu 1. Yeah.
So on 0, 1, you can take derivatives. Because you took nu bigger than 1.
Yes. Yes, because I mean, if you take nu to be 1.5, then you give me, I mean, then that means that guy here is decreasing like a constant divided by nu to, I mean, 1.5 to the j. So that's converging extremely fast, in fact. Of course, as close as you get to nu equals 1, then that's, I mean, then you're starting having problems. But that's where the choice needs to be made in the proof, so that if you would take nu too close to 1, then some bounds will blow up. In fact, I mean, you'll see that on the slides when I will derive the bounds. Yeah. Okay, so how do we do this? So, well, we consider a finite dimensional projection. And that finite dimensional projection is nothing fancy. basically just keep a finite number of Taylor coefficients, and so I'm going to denote it by Fn that goes from Rn plus 1 into Rn plus 1, and that takes a vector A, n, which is A0 all the way to An, so that just keeps n plus 1 Taylor coefficients, and that evaluates Fn of An, which is by definition, well, if I would take the nth component, n goes from 0 to n, by definition this is nothing else than if I take the nth component of f, where I take An and I just put a bunch of zeros. So essentially what it does is that it keeps only finitely many, it considers only the coefficients from 0 to n here and here as well, here, and then that sum will just be the sum from 0 to capital N, and then I have a map that has, and I consider from 2 to capital N, and that's my finite dimensional map. Okay? So for our applications, I think we'll have, the first proof will be with 250, the other one is about 400, and the other one maybe is 5 something. So you can think of this map as going from R3, 4, or 500 to itself. Okay? And then we do, it's a nonlinear problem, so yeah, we better have a good approximate solution to start with. So that was an eigenvalue problem, and then there are theoretical results that says that for some parameter value, then there are bifurcations, and that's what we did. I'm not going to talk about that here, but we used knowledge, of course, from nonlinear analysis and numerics to actually get to compute approximate solution. Because if you have a complicated map and no initial guess, then I mean that's going to be tough. Yes.
So how did you find did you say you find the solutions as a verification?
Yeah, because it's a nonlinear elliptic problem. So by letting there are bifurcation results away from 0. I mean from 0, so you get rid of the nonlinear term, and then there are results. It's very classical, but then we had to transfer these bifurcations into Taylor coefficients, and we used these as inputs, and then after that we applied a continuation, and then we computed some solutions.
Even that I already asked, what happens if you don't have B squared? Like you can, I'm sure that you can adapt it to B cubic. But what about a non-analytic?
Yeah, if we had an analytic map, then we'd have to do something to, let's say, handle.
Let's say you have something analytic like 1 over 1 minus B.
Yeah.
Something like that.
Yeah. Well, so we would have to handle the fact that when we compute, we would have to approximate somehow the 1 divided by 1 minus V, and then control the tail. Yeah, there would be another tail, or we do what Jay is going to talk about tomorrow. We find a smart way to rewrite that nonlinearity as a solution of an ODE, and we append that ODE, and then the problem becomes somehow polynomial again. If, of course, the ODE that is the solution, which has the solution, if the nonlinear term that you have has, is a solution of a simple polynomial ODE, right? Yeah. Okay, algebraic function. Yeah. But anyway, there are several ways to do that. But theoretically, I don't see any big obstructions to actually be able to move in that direction. Okay, so so then we have a map on a computer, and then we apply Newton on some smartly chosen initial guess. Okay, and then we apply Newton, and then we converge, and then close to that, then this is where we want to show that using what Jay talked about. So let's say, what I can do is that I can just define A to be by definition A bar n, which is the output of my Newton, and then I put infinitely many zeros there, and that's an element of my Banach space, right? So now what I want to show is that in a ball centered at that numerical solution, which I computed using Newton, then I have a unique solution locally to that nonlinear operator f in L nu 1. Okay, so for that, I'm going to recall the Newton-Kantorovich type or the radii polynomial kind of theorem soon, but what we need for that is that once we have the numerical solution, we need an approximate derivative. Okay, So approximate derivative of f, and now it's going to be at a bar. And this is where now that becomes fundamentally, that becomes a little bit more interesting in a sense that we have to choose that operator, that approximate derivative, in a way that we can use it for the computation. Okay? So now if you look at the map itself, so when I actually look at that map, there's really one term which is fundamental in terms of being unbounded. It is that term here. Okay? So if I take an element in L nu 1, then by the fact that it's a Banach algebra, that's going to decay very fast because I have a Banach algebra. Same thing here. Well, this is just a guy, right? Okay, so if I have a Banach algebra, then J times A is still going to converge because I will have, but with a slightly less, slightly slower, and I'm hitting it with something that decays like a constant divided by 2 to the J. So, but still, this is kind of going to decrease, right? This is going to decrease nicely. So that's really the part which I want to take care of. And that's really the part which is going to come or appear in the tail of that derivative. Okay? So if you think of the derivative of this now, what is the derivative of that? Well, when I take the derivative, the j nth component is the partial derivative of that with respect to aj. So that's going to lead, when j is equal to n, that's going to be a non-bounded term on the diagonal. Well, when I will differentiate this, okay, I will have some sort of thing involving b, but that's going to decay. So that's going to be, if I think of that in the derivative of that in the off-diagonal terms, that will go to 0. If I differentiate that term, it's like a squared somehow. If I differentiate it, I will have 2 times a, because it's an algebra. So when we do derivatives here, everything is nice because we have algebra. So I will have 2 times a, but a decreases very fast. So when I move away from the diagonal, everything goes to 0. So that really is what I want to think about. This is what I want to keep, okay? So when I will choose that, well, I have choices. And the nice thing is that this is, in fact, an approximate derivative. So, and this is really what Jay talked about earlier on. So for that problem, what we do, since we already have done a lot of work in computing a numerical approximation, and how did we compute that? We applied Newton's method. And in doing Newton's method, we had to code anyway the derivative of f, because that's what we need to do when we do Newton's method. So we already have that, right, computed. So why not to use it? So that's a big n by 1 by n by 1 matrix that sits on the computer. And as I said before, if I had the exact derivative, then I would have, for instance, terms like that on the off diagonal. Because if I differentiate a square, I will have 2 times a, basically something like this, right? Plus other terms. But that goes to 0 when I go away from the derivative. So I can just say, well, I just care about an approximate derivative, so let me just put everything off diagonal to be 0. Okay? Off diagonal to be 0, but I better keep the terms here, n plus 2 square, and all the way n square. And why do I have an n here? Because when I actually take the derivative of that term, there will be an n popping up, n times an popping up, and then that will cancel with this n square minus nan. So there is in that term, in the derivative, there is in fact like an n times an term in here plus something else. So basically, because of that, and that really is just n squared times an. So that's my approximate derivative. Okay. Okay. So this is really the. And now for my approximate inverse, for my a, then what I can do. So that sits on my computer. I can compute a numerical inverse. I don't need to do any interval matrix or whatever. I just do a numerical inverse. And I'm going to call that an, or an. Oh, okay. An is just an approximation for df n a bar n inverse. So that's numerical. So you can ask MATLAB, C++, Julia, whatever, to do it. Sorry to put Julia last. Sorry. So you do that numerically, and that's an approximation, and that can be a very big matrix, but that's just an approximation. And that sits in the memory of the computer. And here, well, I have zeros and zeros, so I just keep zeros, and the inverse I invert exactly. N plus 1 square, 1 over n plus 2 squared, and so on. Okay?
The only matrix we can invert.
Yeah. Yeah. So basically, instead of doing the derivative analytically, we cook up a problem so that we can use the numerics to actually get that big monster. Because for some problem, this is really hard to. I mean, I will talk on Friday about proving existence of periodic orbits in Navier-Stokes, and in that case, that matrix is like 1,000 by thousands and more than that. And if you were to do that by hand, I mean, no way. So, I mean, now this is 3 or 4 or 500 by square. So that's kind of okay. Okay, and that's the approximate inverse of df. Okay, so now I'm ready to show you the bounds. So,
excuse me, I think this is
yeah, maybe we can start.
completely general, like you said, isn't it? So if you have any equation with it's just the highest term, derivative term,
Yeah.
that is going to count.
Yes.
Because it's the term that you need in order to put the boundary conditions.
Yes, I mean.
All the rest is just fine. So.
I mean, it's general. We need somehow some nice structures. So we are using the fact that there is some diagonal dominance in here. Yeah. So that's coming from the fact we have a linear part.
The fact that they are lower terms, and if you assume analyticity,
Right.
coefficients.
I mean, if you think of in terms of classical PDEs, which we already treat a lot with these kind of methods, and we need some for nonlinear problems, we need it to be semi-linear. We need somehow the derivative, the highest derivative to be by itself. And then the rest, if you have lower derivatives and nonlinear terms, then the linear part wins over the nonlinear part, and then you can have a contraction. In some sense, it's very similar to the spirit of Newton, right? So, but it's general up to this point. And it's general up to the point that we can compute, and then we can have, right, I mean, if I have a PDE with a crazy domain, and then I cannot use either Fourier or I have to use finite elements, I mean, you have to be able to compute, and you have to be able to compute with high enough precision so that the bounds that they will show are small enough. And so sometimes if you're forced to take 1 billion variables to compute with to get a small enough defect, and so there's a lot of constraints. So it's not like we are treating everything, but yet we can do a lot of things with that. Yes, I think it's general enough to tackle interesting problems. That's what I think. Okay, so yeah, I'm gonna show some bounds now. And some proofs, so maybe I will. That takes, I think, a little bit of time. Okay. So let me just recall J's theorem. Okay, so at this point we've done everything. We have the map F, we have the Banach space X, we have the approximate solution, we have the approximate derivative of dagger, and we have the approximate inverse A. We have everything. In fact, we don't really need to prescribe y when you think about these kind of problems. We like to put f that goes from x to y, but in some sense, we never.
A brings you back.
Yeah, we never really need. Y. And in fact, when you think about it, what is important is that a times f brings back the space to itself, and that's why we have this 1 over n squared there, because in the tail it hits the n squared. And everything stays now in the space, right? The tail of that operator is chosen so that f maps L nu 1 into L nu 1. And that's really, yeah, it's a smoothing operator. So that needs to be done in a way that we need to choose that. If I chose 1 over n here, that would be an approximate inverse, but that would not do the trick because I would not have my Newton-like operator that Jay talked about would not map x into itself. So there's no way I can do whatever. So that space, that A is really bringing me back to the space. So that's why I say that the Y here is, don't really need to think about it. We just need to choose A so that A times F it goes from X to X. Okay, so now I'm going to compute these 4 bounds in that context. Okay, so let's do it. It's technical, but you know what to do. Okay. So, and it's a school, so let's see, usually in this kind of talk we hand wave and we say, well, believe us, read the paper, but now, sorry guys, it's a school and you're going to have to suffer through the details. Already after all of that details. Okay, so the Y0 bounds, as Jay said, this is a bound for A times F of A bar. F of A bar, it's computed numerically. A is a big matrix and the tail. So when you look, and we have to compute the L nu 1 norm of that. That's an infinite series. But then A has a finite block, so it's hitting the finite block of F, right? So it's basically the finite block. Okay, I guess that would be that notation here. So A times F is the finite block of A times the finite block of F. And then, well, I take the sum n goes from 0 to n of, I mean, that's the finite part of the L nu 1 norm. So that's just numerical. Just numerical, but that's a big matrix times the vector F, in which I have to compute Cauchy products. So I need to do all of that with interval arithmetic. And sometimes, if products are more complicated, as it is the case in Fourier, and if we had cubic or quintic or whatever, I mean, I will have an example with quintic discrete convolution on Friday, coming from periodic orbit in the circular restricted 4-body problem. And in that case, well, we need to compute quintic discrete convolutions, and we use the FFT combined with interval arithmetic. Here it's not so necessary because this is quadratic and this is Cauchy product, so we can actually do it by loops or by Toeplitz matrices or whatever, but that's a computation that needs to be done with interval arithmetic. But if A bar was, I mean, if we computed with a small enough tolerance, then that's going to be, unless AN has a very large, say, condition number, that's going to be very small. That's going to be of the order of the numerical, the tolerance somehow. Well, it depends. If I take nu too large, then, you know, things will blow up. If I would take nu to be 5, then that would just blow up because I have a B, which is not in L nu 5, L5 sorry, so I would blow up. So I have to, I mean, that's where the choice of nu numerically plays a role. You have to choose it so that it's, I mean, it doesn't make this bound too large. Okay, and then the tail, right? Now I have that the tail hits the tail of F. But the thing is that I know that AN is equal to 0 for n greater than n, because I just computed up to some given number. So because of that, the Cauchy product is going to be 0 for all n greater than 2n. Because if you look at the definition of a Cauchy product, and if the input has only finitely many coefficients, then the output will eventually be 0. Meaning that the tail of F will eventually be 0. So I only need to compute the tail of F up to, I mean, because there is a n minus 2 here, up to 2n plus 2. That's another finite dimensional computation. I just implement that on my computer, times nu to the n. And now I have this guy here. And that guy requires doing some estimates because I had the Riemann zeta function. So that's a whole, it's not so hard, but we need to compute and to bound that. So that's actually what I write here. So I said that for very large S, then this is bounded by pi square over 6 for large S. And because of that, we have that the decay rate of BL is less than pi squared divided by 3 times 2 to the minus L. And then we can use that to bound this term here. So, I mean, maybe I will, so that computation here will be in the lecture notes. I don't find it so educative to go line by line. But that tail here, using some easy estimate, you can actually get a bound for that. And I'm going to call that Y tail. And now I'm going to show you how to implement that quickly in MATLAB. So let me open MATLAB. And now I'm not going to do some live coding, but I'm going to show you the actual implementation of that Y0 bound. And in order to compute it rigorously, then I need to start IntLab, because I'm using IntLab, sorry Julia people. And so this is the way to start up IntLab. So when you start it, there is this thing that small little icon. So now IntLab is started, so I can do IntLab interval arithmetic in MATLAB. Okay, so here is now the code that will evaluate the bounds. So maybe I can make it slightly bigger. Preferences, fonts. Let's say maybe 14 is better. Is it better? That's really better, huh? Thank you. Preferences. 18 maybe. Okay, so a bit better. Okay. So what are the inputs? The inputs, okay. So A is a sequence of Taylor coefficients, which are computed using Newton. Lambda is the parameter from the PDE. And then nu is the decay rate. So these are the only input for my computer-assisted proof. Okay, and then I enter in this. And then when I declare all the variables interval, I will have to use a pi there. So I have to basically declare an interval that contains the true value of pi. IntLab knows how to do that. Okay, that's the part where I will actually control rigorously the tail, the coefficients of cotangent. Okay, that's a black box. I will put that code available to you so you can actually run it. The bounds will be in the paper, more details, but that's the part where we compute rigorously the coefficients of the Taylor expansion of the cotangent. Okay, so we need to do that. And at this point, we compute df, the derivative, and we compute an, which is the approximate inverse, just inverting df. That's it. And then, okay, I skip that. Okay, and then basically I need to compute in the z0 bound, I will need to compute basically a times a dagger, and for that I need that to be the exact derivative. So I need a code that does that. So that's going to be an interval arithmetic computation of the derivative. In fact, these are not so complicated as far as codes are concerned. So if you look at just the map f, that's the map f. Okay, so you take lambda and a and b, and then that's a1 equals 0. That's the sum of j times aj equals 0. I define ja is here, okay, and that's my map f. That's basically a 12 lines code for the map f here. Okay, I don't know why that's like this. Okay, so that's my code for the f, and I call that f for Newton, and then I implement the derivative for that. So these are not very complicated codes. Okay, so that's the white tail that I had before. So my white tail, which was basically bounding that part here, well, that's my bound. That involves computing some norm, that involves involving pi square. So that I implement using interval arithmetic. That was the finite part, which is basically an times fn at a bar, plus the remaining sum, which was from basically 2n plus 1 to 2n plus 2, and that's just computed. So I'm going to launch that code. I'm going to stop here. Then for one solution, I'm going to run. So this is basically a proof, a live proof. So it takes some data, and now it computed y0. So y0 is 4 times 8 times 10 to the minus 9, and the nu in that case was 1.06. Okay, well, these solutions are already not so trivial. You will see the amplitude is pretty large, so we could have had some way smaller defect if we chose simpler solutions, but these were kind of at the limit of what we could do. So okay, now the y0, the z0 bound. So if I go back here, okay. So for the z0 bound, I need to compute operator norms. Jay already showed a little bit how to compute these operator norms. So in the case of what we have a finite part and we have a tail here. So when we have something like that, then I can compute the operator norm of such an operator, and this is essentially the max weighted of the L1 norm of each of the columns of the operator. So basically, this is the weighted L1 norm of the finite matrix. And if I have something that decays, for instance, well, then I have just to take the max between the L1 norm of the matrix and the max of the entries, which in that case is just going to be 1 over n plus 1 squared. Okay, so that's very computable for the kind of operators we have. So basically, for the z0 bound, we need to bound the operator norm of I minus a dagger. Because of the way that I chose the tails, then the tail of I minus a dagger is exactly 0, because I'm actually choosing the tails so that, that becomes 1, so that if I do I minus a times a dagger in the tail, it's 0. So that computation here is just the finite dimensional L1, weighted L1 norm of that matrix here, the finite part of the matrix. So that's again a very computable bound. So, and if I go in MATLAB, then my bound is actually, I have a code that does compute the bound of the identity minus an times idf, and that's very quick to do, and I actually get, so that should be a very small, so z, okay, I'm going to skip that. So z0 is 4 times 10 to the minus 11. Okay, so that's the rigorous bound for z0. Now z1, well, for z1, okay, so I need to bound the operator norm of a times df of a bar minus a dagger. So if you look at what that is really, so it's like taking the true derivative minus that part, okay? But the true derivative is basically that and some off-diagonal terms here, okay? So I'm killing when I take that difference here, I'm killing the unbounded term, and that's really important because otherwise I would not have a finite bound. So if I define small z to be the difference given any h in L nu 1 of the action of df of a bar minus a dagger, that's what I get here. So that first term here is the fact that I had a1 in the first part of my f. So that's cancelled by a dagger. And now I just have a tail because in my derivative I just considered or just conserved the finite part of that, and that leaves the tail there. So that's why I have this, because the a dagger did not kill all of that part, it just killed the finite part. So I'm killed with this. But because my h will be L nu 1, that's a converging sequence. I can actually bound that. And for n going from 2 to n, the nth component of that is actually 0, because I have exactly in a dagger the derivative of the finite dimensional part. And in the tail, well, the only part I killed in a dagger in the tail is the unbounded term from my f. So basically when I go here, that's the only part in the derivative that a dagger killed in the tail. So I'm left with the derivative of that. And the derivative of that acting on h, so it's basically this, this quantity here. Okay, so now what I need to do is that I need to bound the action of a times z. So again, this is just a finite computation plus some tail. And then to compute a bound on this, then this is where I'm going to use the Banach algebra. Okay, now I am, of course, there's a lot of stuff I said. It's probably very tiring. And then all I can say is that I will have to bound two things, a finite dimensional part, and I will have to bound a tail. And then using the fact that I do have a Banach algebra, then I can actually get my hands all on these explicit constants. Okay, so I have to take a times z, where z is df of a bar minus a dagger times an element in the unit ball. And when I compute the operator norm to get the z1, then I have to consider all possible h in the unit ball. And because of the Banach algebra, I can eventually get rid of all of these norms. So all of that and the details are in the lecture notes. But basically, the ingredients are Banach algebra and the fact that I control the Taylor coefficients of the BL for large enough Taylor coefficients. So I can define these constants, and then, I mean, that basically provides me an upper bound, a rigorous upper bound modulo computation for, for this. Because this is exactly what I need in order to define the Z1 bound. So we'll give the details in the lecture notes. But once I have these constants, then I just go basically in the code, I implement them, C1, C2, and so on. And then I have, in that case, a Z1 bound, which is 0.42. And that's always the bound which is troubling, because we need that to be less than 1. And as opposed to Z0, which is very small because we have a good approximate, because basically this is a good approximate derivative because MATLAB is smart. Then Z0 is usually very small. But then Z1 is the hard part. Because it's basically saying, well, how much can I really leave? Because when I take an approximate derivative, I leave a lot of terms there. So I need, to control these terms what I left. And that's what Z1 does. And finally, Z2, well, Z2, it's basically analysis. So Z2, I consider that, and then I can compute very easily with the Banach algebra. This is for n for n equals 0 and 1, this is 0, and the rest. So since this is like basically a second derivative, so all of the linear terms will disappear, and I'm kind of left with that. And this is what I have left. And now I need to bound that. I need to have a hitting that part. So now I need an operator norm for a times this. Maybe this is where the Banach algebra is the easiest to see in terms of how useful it can be. So that by definition is the soup when h in L nu 1 norm is less or equal than 1. I computed that guy, so there's a shift here. So the shift brings me a new square, but this is basically now a times c minus a bar star with h. And well, I can put the operator norm up, I mean outside, and now I have the L nu 1 norm of C minus A bar star H. Yeah, C is basically another element in the ball times H, and then this is where I use the Banach algebra. And then this is in the unit ball, and this is less or equal than R. So this is basically my Z2 bound. So Z2 is this, and because I have nice ways to compute operator norms, then that's my Z2 bound. Okay? So this is really where, for instance, we can see easily that the Banach algebra is useful because you can just bound products of vectors, and I know that this is in the unit ball because that's how we compute operator norms, and this is because I needed to compute C, any C in the radius, in the ball of radius R centered at A bar, and that's basically why this is less or equal than R. So that term here is Z2. Okay, so I'm done, and I can go back to the code and just see you computation. So Z2 is now implemented. That's a finite computation, and then in that case Z2 is 7,677. That's not small, but as Jay said, this is hit by R squared. And I have a very small numerical defect. Well, in that case, it was 10 to the minus 9, but that's going to do the trick. So if that quantity here is greater than 0, then, I mean, we are good to go, but let's see, let me just continue. So I did a proof, and the I that I got was this. So for every R in that interval, then I got a proof. That was done with, okay, 250. Okay, so that's the proof. That's a computer-assisted proof. So if you go to the boundary value problem, this is what we proved. So that's V defined on the interval 0, 1, and that's a Taylor series. That's the function that represents the Taylor series that we computed with 250 Taylor coefficients. And that, on the right, this is the corresponding radially symmetric solution on the 2-sphere of unit 1, okay? So that was a first proof that we did. Another one, let's say if I continue that code. So for the second one, we took a 410 Taylor coefficients. That's my interval radius. So with C0 bound of 10 to the minus 7, then that's the solution. So you can see here that the amplitude was pretty large. So I mean, the Taylor solution here is I mean, that's a pretty high, I mean, pretty big amplitude for one Taylor, right? But still, the proof worked, and that's what it represents in terms of solution of the sphere. So these are proofs, I mean, of steady states on the Laplace-Beltrami nonlinear elliptic problem on the sphere. And finally, a last one. So in that case, that was faster because we have how many modes? 260. So that's the solution. That was faster because we had less amplitude, so things were a little bit easier. So that's another solution, and that's this one. So all of these are computer-assisted proofs, and in fact, for that, what was 10 to the minus 7. I mean, this is pretty tight, right? I mean, that's a proof, but you know, that's a very tight proof, because if we take R greater than that value, then we do not have a contraction. So let's say that gap where we cannot take R too small, because if we take it too small, then we'll be away from the numerical solution, and if we take it too large, then we don't have a contraction. So that's why these polynomials are useful, because you can see here that's a very small window. So if you just try to do it by ad hoc method, then yeah, that's hard, because you can see here that there's not a lot of room for errors. Okay, I mean, I know it was a lot of details, and all of the bounds and all of that setup will actually be in the lecture notes that Renato will have. The code that produces these pictures and the proofs with interval arithmetic will be also provided to Renato. And there's another problem in that set of notes, and I think that for that second problem, there would be some potential extension using different setup, and I would be happy if some of you guys want to look at the lecture notes, look at the second problem, which is to some extent easier than what I talked about today. You know, we did only one Taylor, but I think that by doing a couple of Taylors or domain decompositions in Taylor, we could do some more interesting computer-assisted proofs for this other problem. And the other problem in that lecture notes is steady states of Swift-Hohenberg, but on the ball, on the 3-ball. And yeah, so basically the assignment, for those of you who are interested, you could go in the lecture notes, look at the second part of the paper using exactly the same philosophy, and then we got proofs there, but we could get more interesting proofs if we changed a little bit the setups. I would be happy to talk about that if you have questions later on this week. Okay, so I guess I'm tired.
Quick questions for Jean Philippe.
I have a quick question. Sorry, I missed that. What's the difference between these three solutions?
This what?
What's the difference between these three solutions?
Yeah. So one of them is that lambda equals, so it's the parameter value. So that's So that's the basically when I talk about the notes, this is the notes I have in mind. So that's this computer-assisted proof for radially symmetric solutions of PDEs that involve 3 or 5 grad students who were in Vancouver and 3 professors. We wrote a paper about what we did back then. And for this, I mean, that's basically all the tedious bounds are all there. And so for the first solution, it was at the parameter value 5.67, the second one at lambda equals 20, and the other one at lambda equals 19.961. So they were coming off different bifurcation branch. And on each of the bifurcation branch, at some point, the radius of convergence became less than 1, and then we couldn't prove. So we got basically as far as we could on the branch, and we put the nicest solution along each of the branches.
So you have computed the bifurcation diagram?
No, we are not computing the bifurcation diagram
just,
at a single parameter value. Yeah, we could.
But numerically, you computed.
Yes, but we could do. We could compute branches if we were doing more work.
Yeah,
if
I can imagine.
Yeah, if we were to do the uniform contraction theorem instead of the contraction mapping, now you have to do uniform contraction in the parameter lambda. So instead of having one solution, then you would have branches of solutions, and instead of using contraction, you use the uniform contraction. So all of the bounds that I talked about can be y0, z0, z1. They can all be done, but now uniformly in the parameter.
Okay. So just a really quick one. So that means that for these lambda values,
Yeah.
They were found just by chance, or just?
So as I said, for these, they were branches. They were bifurcation branches out of u is equal to 0.
I see. Okay.
That's the steady state of the PDE. If you look at the PDE, there's u everywhere, so u equals 0 is the solution for all lambda. And if you look at the kernel as a function of lambda, there are bifurcations, and we bifurcated, and from 3 branches, then we computed numerically all the way to what we could prove.
Okay.
And then that's the best we could do. And in fact, that's the best we could do under the assumption that we think that we assume that solutions could be proven using one Taylor. Now with a student, I'm actually using Taylor and Chebyshev for that first problem. That's why I do not encourage you to look for the first problem, because I'm doing that. But the second problem, so these are the solutions, but the second problem where we have this, quickly, yeah, this is like the Swift-Hohenberg PDE, but now on the unit ball. So I think on the unit, disk in R3. So that's still a reaction diffusion posed on the ball, and we have, exactly similar things, and this is also, say, computer-assisted proofs. Then the amplitude is pretty high, but we did one Taylor, and I think for that, because there's no cotangent, it's just a system, so you have to deal with systems. But for that, we could get, if some of you guys are interested, I would be happy to actually go back to that PDE, change the setup, do more domains, and then we could get more different proofs for already something which is kind of out of reach for the nonlinear analyst. When you get away from bifurcation, then you have a 3D PDEs. Even though if these are radially symmetric, you could get very nice new results if you were willing to spend more time doing fancier numerics than what we did here. Yeah.
So I guess we could also keep asking questions tomorrow and the day after and next week. So thanks a lot to Jean Philippe and Jay for today's lectures. Tomorrow you're at 4. Nos vemos mañana aquí a las 4. Mañana también es de 4 a 7. Van a hablar los dos y el viernes será la tercera sesión. Bueno, pues muchas gracias.